Okay, we're in the fourth video. We're talking in this chapter about calculations from a chemical equation. So doing stoichiometry, doing calculations and conversions given the quantity of one reagent, and you have to calculate the quantity of a different reagent. And what we found in the chapter is that you have to go through the balanced chemical equation. You have to look at the mole ratios to convert from one reagent to the other. In this video, we're going to be talking about the topic of limiting reagents. And before I get started on telling you about what those are, I'd like to just do an example. So let's say you're going to make a sandwich. When you go to make a sandwich, you need certain ingredients. The first thing you need 2 pieces of bread, right? One on top, one on bottom. And let's say that I'm going to make a certain sandwich my way. So let's say that I'm going to make the ultimate grilled cheese sandwich. So I've got 2 pieces of bread. I like to put in 3 slices of cheese. Okay, let's just say that that's the recipe. It's a special grilled cheese sandwich. So 3 slices of cheese. And we'll also need, let's say, a tablespoon of butter to butter on each side. So 1 tablespoon of butter to butter each side of your bread, and you're going to grill it up and you're going to get 1 sandwich. Okay, so you've got 1 sandwich there. That's the recipe for a sandwich. Let's say you go to your cabinet, your cupboard, you go to the refrigerator, and here's what you've got. You've got 13 pieces of bread, slices of bread, I should say. 13 slices or pieces of bread. And let's say you have 8 slices of cheese, and you have 6 tablespoons of butter. Okay, so you pull it out, and you're like, I wonder how many sandwiches I can make with this. Okay, let's get started. For every 1 sandwich, it takes 2 pieces of bread. So if we were looking at the bread alone, you have 13 pieces or slices of bread. How many sandwiches could you make from that? Whole sandwiches, not half sandwiches. Okay, so 2, 4, 6, 8, 10, 12. So you could make 6 sandwiches if you were only looking at the bread, right? Because I could make 6 sandwiches out of this, and then I'd have a slice left over. All right, how many sandwiches could you make if you just looked at the cheese alone? All right. So if I have 8 slices of cheese, you need 3 slices of cheese for the ultimate grilled cheese sandwich. So let's see here. If I have 8 divided by 3 is 2 point something and some change. So we've got 3 for the first, 3 for the second. So you can actually make 2 sandwiches from this recipe because you'd have 2 left over. You wouldn't have 3 slices left over. So you can only make 2 sandwiches from the cheese. Now, how many sandwiches could you make from the butter? Well, 1 tablespoon of butter makes 1 sandwich. You've got 6. So 6 divided by 1, you can make 6 sandwiches. You can make 6 sandwiches. All right, now out of this, if you put all these ingredients together, the 13 pieces of bread, the 8 slices of cheese you have, and the 6 tablespoons of butter, given all of them combined, could you seriously make 6 sandwiches? No, because you don't have enough cheese. The maximum number of sandwiches you could make would be 2, because you're limited on the amount of cheese you have. And if you made 2 sandwiches, you would have excess bread, you'd have excess butter, but you can only make 2 sandwiches because you only have 8 slices of cheese. All right, this is an example of a limiting reagent problem, and it's a little simplified, I know, but basically this is what we're talking about. So in this section, when we talk about limiting reagents, we're talking about chemical reactions, not recipes. But it's kind of the same example. You've got things going in and things coming out. When we talk about limiting reagents or limiting reagent problems, there's always 2 terms you need to know. The first is the limiting reagent. What is a limiting reagent? It's the reactant in a balanced chemical equation. So how much of the reactant that you actually have in that equation that limits the amount of product that can be made. Like the cheese in the previous example. You had hardly any cheese, so it limited the amount of sandwiches you could make. So limiting reagent limits the amount of product that can be made. Whenever the reaction stops, the limiting reagent is usually always consumed. There's no more remaining. The reagents that are left over after the limiting reagent has been consumed are called the excess reagents. An excess reagent is a reactant that remains when the reaction stops. So there's always leftover reactant. An example of this is all that bread or all that butter that was left over after all the sandwiches were made. So if you're given the quantity of several of the reagents, so if you're given, let's say you have reaction A plus B goes to C. If I was just given the quantity of one reagent and didn't know anything about the quantity of the other, if I asked you how much product you could make, if you only knew the quantity of B, you could only use that quantity to determine how much C you can make. Well, in this series of calculations that we'll be doing today, we're going to be given the quantities of A and the quantities of B. So what we're going to be able to do is we're going to be able to do that stoichiometry problem, the conversion using stoichiometry, twice. Because we can say, well, how much product would I make if all of my A reacted? How much product would I make if all my B reacted? And just like we did with the sandwiches, you compare how much product you would make. Whichever reagent makes the least amount of product is the limiting reagent. The one that makes the most product would be the excess reagent in the reaction, and it would not all be consumed. The limiting reagent would be consumed, and the other reagent, there would be, after it reacted with the limiting, there would be more left over. It's important to say that when we look at these reactions, the limiting reagent does not mean it's the reagent in least quantity. You have to look at the mole ratio of the reaction in order to see which one's the limiting reagent. All right? So let's get started and do some problems. Okay, so actually I lied. Before we start problem, let's look at this problem, because this is one that your book gives and I really like it. So it says, what is the limiting part in the production of these bicycles? So let's say you're making a bicycle. We've got 3 different parts here. The first part we have given are the wheels. Whoops. We've got the wheels. We've got the frames, and we've got the pedal assemblies. So for every bike, you need 1 frame. You need how many wheels? We need 2 wheels. And the pedal assembly comes with both pedals and all the gear stuff. So you need 1 pedal assembly. Okay, so that makes 1 bike. That'll equal 1 bike. So the question was, what is the limiting part in the production of these bicycles? Well, let's see how many bikes we can make first. If I'm going to make a bike, I'm going to start with my frame. So I've got 1 frame. I'm going to need 1 pedal assembly. And I'm going to need 2 wheels. Okay, so that gives me 1 bike. Let's do another one. We've got a frame. We've got a pedal assembly. And we've got 2 wheels. So that's bike number 2. Let's make another one. We've got a frame, a pedal assembly, and 2 wheels. That's 3 bikes. Can we make a 4th bike? We've got a frame. We've got 2 wheels. But I think you noticed we have no pedal assembly. We ran out of pedal assemblies. So we've got an extra set of wheels. We've got an extra frame. But we have no more pedal assemblies. Because we ran out, at the end of our production line, we ended up with 3 bikes, but we also ended up with 2 wheels and 1 frame. The limiting parts, or the limiting reagents, is what we're looking at, would be the pedal assembly. We didn't have enough of those to make a 4th bike. It was the limiting part. Once all of that part was gone, that's as much of the product, the bike, we could make. The excess parts, or the excess reagents, were the wheels and the frames. When we finished making 3 bikes, we had 2 wheels and 1 frame left over. Okay, so that's pretty much what we're doing here. We're going to look at the quantities of reagents, the reactants. In problems that are limiting reagent problems, how do we know we're going to have limiting reagent problems? It'll look just like a regular stoichiometry problem. However, instead of being given the quantity of 1 reagent, you'll be given the quantity of at least 2 reagents. When you're given 2 different quantities instead of 1, what you're going to do is you're going to figure out which one's limiting by converting them both to amount of product and saying which one of these makes the least amount of product. The one that makes the least amount of product is always the limiting reagent. The one that makes more product would be excess, and you can calculate how much of that you have. So the answer is to always convert what you're given to the product and compare the quantity of the products. The one with the least amount of product converted would be your limiting reagent, and that's the amount you can actually make. The amount you actually make is called the theoretical yield. So let's say that I have A plus B yields C. If I'm given the quantity of A and I'm given the quantity of B, and somebody asks me, how much C would you make if you have this much A and this much B? What you're going to do is you're going to convert the quantity of A to the quantity of C, perhaps the moles of C that be produced, or maybe the mass, whatever the question asks. You're also going to convert the quantity of B to C. So how much C? So we'll say C from B, and how much C from A you would make. You're going to compare the lesser amount of C made is called your theoretical yield. Your theoretical yield. Whichever quantity A or B produces the least amount of C is your theoretical yield. It's the amount that you could, if all of the reaction went to completion, that you theoretically could make. Whichever the lower yield is, that reagent that made the lower yield is called the limiting reagent, and the other one's in excess. So let's look at some problems where you can really apply these terminology and understand how to solve some problems. Alright, so here's an example. This problem says calculate the number of moles of water. So we wanted to calculate the moles of water. That's our unknown here. So how many moles of water can be made from the reaction of 1.51 moles of hydrogen with 0.932 moles of oxygen? Alright, so how do I know this is a limiting reagent problem? That's going to be the hardest part for you, figuring out how to solve the problem. It's not really that hard, I promise. You see how we're given 2 knowns? We're given 1.51 moles of hydrogen and we're given 0.932 moles of oxygen. Well, those are both 2 knowns. Those are both reagents. This is a limiting reagent problem. We want to know how much product we can make if we combine these 2 reagents. So what we want to know is which one is the limiting reagent. The limiting reagent will make the least amount of product, and that's your theoretical amount of product that you're going to make. Okay, so how are we going to solve it? Here we're given moles of hydrogen. We need to convert moles of hydrogen to moles of water first. So from the hydrogen, we're going to calculate the moles of water. Because we're also given oxygen, we're also going to convert oxygen moles to water moles, and we're going to compare those 2 answers. So let's start with the hydrogen first. We're given 1.51 moles of hydrogen. How many moles of water can we make? Well, we're already in the mole, so we're going to do a mole to mole. In this reaction, for every 2 moles of hydrogen, we produce 2 moles of water. So for every 2 moles of hydrogen, we produce 2 moles of water. Okay, so I've got my moles of hydrogen on top. That's why I put it on bottom, so they'll cancel out, converting 2 moles of water. Notice I've also got a 2 on top and a 2 on bottom. Those cancel out as well. Basically, what I say here is that for every mole of hydrogen, I make a mole of water, right? So I should make 1.51 moles of water from the hydrogen. Okay, now notice for a limiting reagent problem, because I'm going to be converting to moles of water twice, I always remind myself where that quantity came from. So this is if all the hydrogen reacted. Now let's do it for oxygen. We have 0.932 moles of oxygen given. We say, well, if all of that oxygen reacted, how many moles of water could I make? Well, in the balanced chemical equation, for every 1 mole of oxygen, so oxygen on top, oxygen on bottom, I make 2 moles of water. So I'm going to get my calculator out here. I don't trust myself. 1.86 something. All right. 0.932 times 2. Hey, I should have trusted myself. 1.864, but it's late for me, so 1.864, and it looks like 3 significant figures here, so I'm going to say 1.86 moles of water could be produced from the oxygen. So if all the oxygen reacted, I could make 1.86 moles of water. And then my next question is, wait a second, I can only make so much water. It asks me how much water I can make. I can't make both quantities, I can only make one. We're always going to make the lesser quantity. The amount made that could theoretically be made is always from the limiting reagent. So because this is the lesser quantity, 1.51 is less than 1.86, this is going to be called my theoretical yield. This is the theoretical amount I could probably make when these are combined. And the theoretical yield, the lower quantity, always comes from the limiting reagent. So hydrogen is my limiting reagent, which means that oxygen is in excess. It's my excess reagent. What does that mean? Well, when the reaction's over, when I produce a theoretical amount of 1.51 moles of water, that comes from all of my hydrogen being consumed. My limiting reagent, hydrogen, there'll be no more present in the reaction flask. It's going to be gone. How much oxygen will be remaining? It's the excess reagent, so there's going to be some left over. We can actually calculate how much oxygen will remain when the reaction stops. So first of all, the answer, my theoretical yield, was 1.51 moles of water. Okay. My limiting reagent was hydrogen. So when the reaction stops, there will be none left. It's all consumed. So there will be no moles of oxygen left. It's my limiting reactant. But for my excess reactant, which was oxygen, how much will be left once the reaction's completed, once all of the hydrogen reacts? The way we're going to solve this problem is to figure out how many moles of hydrogen or oxygen are consumed when we produce 1.51 moles of water. So let me remind you of what the balanced chemical equation is real quick. The balanced equation is for every 2 moles of hydrogen and 1 mole of oxygen, we make 2 moles of water. Okay? So now I'm going to reverse the stoichiometry. If I make 1.51 moles of water, how many moles of oxygen were consumed? I'm just going to do a reverse stoichiometry. Instead of figuring out the product, I'm going to figure out how much reactant was consumed. So this time I'm going to take my theoretical yield, 1.51 moles of water. Okay? If all of that reacted, for every 2 moles of water that were produced, how much oxygen reacted? Well, 1 mole of oxygen reacts. So let's get our calculator out here. We've got 1.51 divided by 2, 0.755. So 0.755 moles of oxygen would have reacted, or would have been consumed. Okay, so we want to know how much oxygen is left over after the reaction takes place. Well, let's go to the next page. The moles of oxygen left, or in excess, after the reaction takes place is going to equal the moles of oxygen given minus the moles of oxygen consumed. Okay? Now, the original problem, because you probably are like, I don't remember how much is left. In the original problem, there was 0.932 moles of oxygen given. We just calculated that if we made the 1.51 moles of hydrogen, if all of that hydrogen, or water, if all of that hydrogen reacted, that we would have used 0.755 moles consumed. So basically, we take the amount that was given, 0.932, we subtract the amount that would have reacted to make that theoretical yield, and we end up getting 0.177 moles of oxygen left, or in excess. So that would be how much was left. Okay? So let's kind of look at this pictorially. Let's say that we had 0.5 moles of hydrogen. All right? And we said that we added 0.9, so let's do 0.2, 0.4, 0.6, 0.8, 0.9 moles of oxygen. If we were going to produce 0.5, 0.5, 0.5 water here, let's see what happens. So we said that if we reacted 1.51 moles of hydrogen, that's roughly 0.51, 1.5. If we reacted 1.5 moles of hydrogen, we would make 1.51 moles of water. 0.5, 1, 1.5. All right. Now, in order for that to occur, for every 1.5 moles of oxygen we use, or hydrogen, we said we used half the amount, because it's 2 hydrogens plus oxygen yields 2 waters. So half of 1.51 is 0.755. So 2, 4, 6, 7. We'll say that. So how much is left over? This is excess because it didn't react. So this would be left over when our water was produced. Okay, that's what it means. Let's try a different reaction. Okay, another limiting reaction problem, and we'll look why we know it's that when we read it. It says, what is the mass of silver? So we want to know how many grams of silver, which is a product here, is produced by the reaction of 3 moles of copper. So we've got 3.00 moles of copper with 3 moles of silver nitrate. So we've got 3.00 moles of silver nitrate. Okay, now how do I know this is a limiting reagent problem? Well, once again, I'm given the quantity of copper, and I want to know how much product it can make, but I'm also given, the second reagent. the amounts of silver nitrate. Because I'm given the quantity of 2 reagents and asked to figure out how much product, I need to figure it out. I need to figure out what my theoretical yield is by figuring out the limiting reagent. Whenever you're given 2 reagents, there's always usually a limiting and an excess. So once again, how do we figure out which one's limiting and which one's excess? We're going to convert the copper and the silver nitrate both to grams of silver, and then we're going to compare those and see which one makes the least amount of silver. So we've got 2 reagents. Here we've got copper, so I'm going to start with copper. And then we've also got our silver nitrate, AgNO3. All right, we're going to convert the quantity of copper, 3 moles, to grams of silver. So can I go straight from moles of copper to grams of silver? No, what must I always go through? The mole. So the first I'm going to convert moles of copper to moles of silver. Notice that for every 1 mole of copper, which I'm going to put in the denominator here to cancel out my copper, for every 1 mole of copper, we make 2 moles of silver. Alright, and then from my moles of silver, I can then calculate how many grams of silver that would make us. Now in the problem, we're given the molar mass of silver. So we can convert moles of silver cancel those out. My moles of silver to grams of silver using that molar mass. Okay, so we can calculate that. Given that we're given 3 significant figures here at the beginning, when I got my answer, it was 647.22 grams of silver. I just rounded that to 3 significant figures, so 647 grams of silver. If I reacted 3 moles of copper in this reaction, and all 3 moles of copper reacted, they were all consumed, I would yield 647 grams of silver. Alright, now let's do the same calculation, and let's assume now that all of the silver nitrate reacts. So we're given 3.00 moles of silver nitrate. Now, before we get any farther, some people will say, this isn't a limiting reaction problem, I have the same amount of each reagent. Yeah, you have 3 moles of copper and you have 3 moles of silver nitrate. However, in the reaction, do you need 1 equivalent of each? No. For every 1 equivalent of copper, you need 2 equivalents of silver nitrate. So notice it's not a stoichiometrically equal ratio when we say balanced. So once again, we're going to have to figure this out. So let's just go back to what we were doing now. We were going to assume all of the silver nitrate reacted. If we have 3 moles of silver nitrate, first we're going to convert that to moles of silver, just like we did before. We want to figure out how many grams of silver we can make, but we have to go through the mole. So in this reaction, for every 2 moles of silver nitrate, why am I putting this on bottom? Because I've got a moles of silver nitrate on top. I want to figure out how many moles of silver I can make. And it looks like in the balanced equation, it's 2 to 2, or 1 to 1. So I'm going to actually cancel those 2's out. That'll make my life easier. Oops, we're not ready yet, are we? Okay, so I've converted moles of silver nitrate to moles of silver using my mole ratio. And now I want to convert that to grams of silver. Now I can get out of the mole, right? So I'm going to use my molar mass here. For every 1 mole of silver, on the periodic table it tells us the same thing, there's 107.87 grams of silver. Okay, so we're just going to calculate it. Okay, from all of my silver nitrate reacting, all 3 moles, I calculated actually 323.61 grams of silver, but I rounded that because I have 3 significant figures here to 3 significant figures my answer. So we would make 324 grams of silver. So are we going to make 647 or are we going to make 324 grams of silver? Well, you're not going to make both. You're always going to make the lesser amount. So what is this reagent or this quantity called? The lesser quantity of product you made? It's called the theoretical yield. All right? So theoretically, this is how much silver we would make. What does the question ask us? It says, what is the mass of silver produced? The theoretical yield, the amount of silver produced in this reaction, if you combine the copper and the silver nitrate, would be 324 grams of silver. That's the product. That's your theoretical yield. All right. Because the theoretical yield came from all of the silver nitrate reacting, silver nitrate then is called the limiting reagent. The copper then would be considered the excess reagent. All right? It would be the excess reagent. All right. So can we calculate how many moles of copper would be left after the reaction was completed? Yeah, let's go the extra mile and do that. Okay, so we said that I'll put the reaction back up. In the reaction, we've got copper plus 2 silver nitrates. And we didn't really care about the copper nitrate, but we got the copper nitrate plus the 2 silvers. So there's our balanced chemical reaction. We said that our theoretical yield was 324 grams of silver. If we know we're going to make 324 grams of silver, we were given, 3.00 moles of copper. How much copper is consumed? Which means how much of this copper reacted to give us 324 grams of our product? Well, we can actually calculate how much of this copper was consumed. We're going to start with the 324 grams of silver. We can convert that back. So remember the molar mass of silver, if we've got grams of silver, there's 107.87 grams of silver for every 1 mole of silver. So I'm going to convert my grams of silver back into moles of silver, so then I can do my mole to mole conversion. So now that I've got it into moles of silver, use my molar mass there, I want to convert moles of silver to moles of copper. I'm going to use my mole ratio. For every 2 moles of silver, silver on top, silver on bottom, or bottom on top, how many moles of copper were consumed? 1 mole of copper. Okay. So now I've converted to moles of copper consumed. So I'm going to calculate this. I've got 324 divided by 107.87 times 2, and I get 1.50. 187. It keeps going. But I get about 1.50 with 3 significant figures moles of copper. Okay? Consumed or used up. If I started or was given 3 moles of copper and 1.5 moles of copper was consumed, how much copper was left? Well, copper left, or then the excess amount of copper is going to equal the copper given minus the copper consumed or used. So it would be 3.00 moles minus 1.050 moles, which is 1.5 moles left. So we'd have roughly 1.5 moles left. I'm just extending the problem. The problem didn't ask for all this. But from a limiting reagent problem, you can get so much information. You can learn how much product you're going to make, the theoretical yield. From that, you can determine how much limiting reagent is left, which is always 0, by the way, because you know which one the limiting reagent is. And then from there, you can also figure out how much of the other reactant was used up and how much was left in your reaction mixture at the end of the reaction. All right? Okay, so that's limiting reagent. In the next and last video, we're going to talk about percent yields. So we're going to need to know what a theoretical yield is for that.